Thank you, Quentin. So I'm going to be talking about one of my dissertation chapters where I've looked at long-term growth data in Virginia. I'd like to thank my co-authors for all their work on this, as well as Virginia Sea Grant, who's funding a lot of this work. So blue catfish were introduced to the Chesapeake Bay in the early 70s, beginning in the Rappahannock River in 1974, the James River in 75, and the Mattaponi River later in 1985. From that, they've moved on to the Pamunkey River. They were first collected there in 1988, but they've also moved all these systems that are depicted in brown, and they've also been collected out in the middle of the bay, which has been found by Mary Fabrizio's group at VIMS. And based on some work that Bhaskar, Nepal, and Mary have done, they found that really there's no barrier based on salinity in the bay for their dispersal. And so not only is this ability to expand their range concerning, also this is a very abundant species in the Chesapeake Bay region. You can see me poorly trying to net all these fish. And so there's been 2 studies looking at abundance of blue catfish in Chesapeake Bay tributaries. Both of those are in the James River. One in Fowl Creek, is a tidal tributary to the James River, and then also one in the mainstem James. And to give you an idea of how much space we're looking at, Fowl Creek's about 3 miles, and this section of the James where the study was conducted by Mary's group is about 7.5 miles. And what those studies found, the study in Fowl Creek was done over 2 years, 2007 and 2014, and found there were close to 30,000 and 10,000 fish respectively. Mary's work found about 1.6 million, estimated about 1.6 million fish from 9 to 18 inches fork length, so pretty dense populations that we're talking about here. And with that, this generated a lot of concerns for alicines, which are at risk and they have harvest moratoria. Atlantic sturgeon, blue crabs as well, given its iconic status in the Bay region. A lot of concern for these species, as well as many others, including non-native fish like the largemouth bass. A lot of folks think that blue cats are eating all the largemouth bass. But that's kind of contrasted with the fact that blue catfish provide recreational fishing opportunities, both folks that are more harvest-oriented and more trophy anglers, which supports a pretty popular guide industry in the Chesapeake Bay region. And again, contrasting with that, kind of more so adding to the complexity of this situation is that they now support commercial fisheries that recently have harvested over 1,000 metric tons of blue catfish. And so an important aspect of trying to figure out how to manage this species is size and growth rates. In terms of Virginia's trophy fish citation program, you can see it's largely dominated by the James River, and there's been a pretty steep decline in the number of citations reported. Part of that could be reduced reporting rates as folks get enough of these things enough of the trophy fish certificates on the wall. You're not going to send $5 in for much longer, I wouldn't think. So there could be some of that, but we've also noticed that growth rates are highly variable, and there seems to be some patterning spatially based on rivers. And size is also important in blue catfish management in Chesapeake Bay, because we found out of some diet work at Virginia Tech that diets differ by size groups for fish, and there's an ontogenetic diet shift. So that set up this need to better understand growth rates in Virginia blue catfish. We looked at 4 river systems, the James, Rappahannock, Mattaponi, and Pamunkey rivers, and we wanted to understand how growth variability is partitioned over time and space. So we also wanted to, based on some previous work by Bob Greenlee and some things that we noticed just plotting the data out, we wanted to determine if growth rates had declined over time, and how does inference change for native versus non-native growth rates in relation to time. So a lot of the work that's been done previously has looked at whether native or non-native fishes grow faster, and the results have been somewhat inconclusive. So we wanted to look at how time may influence the inference that you can make based on that. And so our hypothesis here is that early in the time series, abundance will be lower, and so we'll see faster growth and bigger fish. But as populations mature, densities increase, we'll likely see slower growth rates. That's kind of what we were thinking here with this. We also suspected that there would be differences among river systems. As the Rappahannock and James rivers were stocked first, we expected that growth rates might be a little slower there based on the fact that they were stocked earlier and would likely have higher densities. So to kind of show you again where we're looking, so this is the James River. The Pamunkey and Mattaponi rivers are a little bit north of that. They converge to form the York. So if I mention York tribs, that's what I'm talking about, the Pamunkey and Mattaponi together. And the Rappahannock's the furthest north, and again, that's the earliest stocked population. And so in terms of our growth analysis, we developed 6 alternative hypotheses. Homogeneity in growth, we just lumped all the data in one model fit. Growth varying by river, year, cohort, and then the combinations of river, year, and river cohort. And we evaluated this using nonlinear mixed effects models, where we were able to specify random effects of each of our components of our hypotheses and compared these models based on AIC. So we also did some trend analysis to look at whether or not mean length at age had declined over time. And we looked at ages 1, 4, 7, 10, and 13 based on where we had data in the Pamunkey River. Given that it's the most recently established population, we couldn't really expand beyond that. We have fish out to 25 years, but the data are a little scarce, getting out much farther than 13. And so in comparing native versus non-native growth, we looked at 12 native populations. We tried to find published studies that used otoliths to determine ages, and so that kind of limited us into a fairly small number of papers that we could use. And we just did a visual comparison just to show how inference might change over time. We also did a quick synchrony analysis, which I'm not going to talk about much, but I will mention it later. So here's our, that shifted on me. So here are our hypotheses again to remind you, and based on these modeling results, here are our AIC rankings, and the river cohort model was the most supported model, and that corresponds to the hypothesis that growth varies by river and cohort. And if we look at the results, these are the von Bertalanffy growth parameters. You can see a decline in James and maybe a modest decline elsewhere, but still some noisiness that kind of supports that there are variability within cohorts beyond what we see with the trends. I will note that you see kind of an increase early in the time series and at the end. We believe that this is due to the fact that moving further along in the time series, more large fish become available and kind of move the growth curve L infinity parameter up. And at the end of the time series, this is based on fish with a relatively short age frame, and so we believe that those fish have a little bit of uncertainty in where that curve's being fit. And so given that L infinity and K are negatively correlated, we kind of see the opposite trends with K. And so we'll also look at the river year model. It wasn't the best model, but it's a little easier to think of conceptually, and it's a little easier to plot, honestly. With the cohort model, we had about 114 groups of rivers and cohorts, so this is a little easier to present. And this also covers the entire age range. With the cohort model, we're kind of limited to chunks of the age distribution. And so we see declines in the Pamunkey and Mattaponi for L infinity, as well as the Rappahannock, although this was a year with a small sample size, so it's a little bit more uncertain. The James is a little noisy based on this. And this is probably the most panels you can fit on the screen. So this is the fitted values for the river year model, and also just the data that we fit the models to. And you can see there's kind of some odd shapes on the data. We believe that's possibly due to 2 reasons. One, this could be evidence of that time variant growth where fish grew faster, and then the more recent fish are growing slower. Could also be related to some bias in the sampling. But if you look, so these are the James River years from 2002 to 2016, and you can see over time that these fish out to about age 10, they kind of bend and are growing much more slowly than they were over here. And that's kind of the same pattern in all four rivers. Mattaponi begins here and ends here, and you can kind of see the same pattern. And I apologize for putting 32 panels up there, but it had to be done. So kind of to show you this together with the earliest year and the most recent year that I examined, 2002 and 2016, you can see that there is a considerable decline in growth rates when you look at the data longitudinally. And so in terms of our trend analysis, this is the mean length of age plotted for 5 age groups that we looked at. You can see generally there are declines. There were not statistical declines in age 1 in the Rappahannock, age 4, and age 13. All other trends that we looked at were statistically significant. In terms of looking at native and non-native growth, we looked at, these are the populations, the locations of the populations we looked at. Baden Lake and Lake Norman in North Carolina, and the Altamaha River, and then our 4 Virginia populations. Most of these are in Oklahoma, and then some in Tennessee also. And so here, what we looked at are visual comparison. So these are all the native populations plotted out, and the gray shading in the background is the extent of those native populations. And you can see that Baden Lake and the Altamaha River grow much faster than most of the native populations. Lake Norman's kind of in the middle. But when we look at the Virginia populations compared to native populations, inference kind of changes depending on which year you're talking about. So, don't do that. So you can see it goes from growth is faster or as fast as some of your faster growing native populations, but as the populations mature, it's more average or less than average in the case of the Rappahannock. So we think that's something we need to consider moving forward when we're comparing growth rates among native and non-native populations of species. And so for conclusions, growth rates varied over time and space, which then supports that when we're considering growth rates and population assessments to evaluate control measures, we need to consider how growth rates could change and do some sensitivity analyses. This is supporting a development of a population dynamic model, and so we've included time-varying growth in that, so this was extremely informative for that. Declines were common in mean length of age, but it was least likely in the Rappahannock. Again, that was the river that was stocked first, so we believe that it's likely stabilized prior to the other systems. And again, I didn't mention the synchrony analysis much, but we did find that in most cases, we looked at 35 pairwise river comparisons based on residuals from our trend analysis, and found that in most cases we were unable to detect synchronous responses for the entire for the mean length of ages, and so we believe that there's an important contribution of fine scale factors in determining growth rates. And again, in terms of native and non-native comparisons, time may influence inference and maybe something we should consider moving forward. And so I got to put in a quick plug for my blog. So this is the ChesapeakeCatfish.com blog. I share a lot of just summaries of published studies and some more fun articles. I wrote an article about how to avoid getting duped by online catfish tales. So I'm sure a lot of you have seen somebody will post a picture of a Wells catfish and say it was collected in the Ohio River or something. It's 290 pounds, and people lose their minds. So just kind of giving anglers guidance on how to avoid getting duped, but also sharing some science as well. So if you have anybody that's interested, feel free to, or please share that with them. I'd like to thank all the folks that have been a part of this work, either funding it or actually doing the work, especially folks that collected all the age and growth data, and this list of folks that have looked at this paper at some point. And I'd especially like to thank the Fish Management section of AFS for providing a travel award, and I'll take any questions that you may have.